All right, good afternoon, everyone. As we saw, I don't know how many of you guys, maybe many of you guys saw Alexis's keynote today morning. As Meta brings almost half the population to their services through Facebook and Instagram and WhatsApp, almost 3.65 billion people, right? And the vision of Metaverse. All of these services that Meta brings play a crucial role. The infrastructure plays a crucial role. There is a significant dependency on that as we try to get the performance and the scale and the reach for all these services. So what Chris and I want to focus today is the role of memory in this all infrastructure. And today's data center, how we design from memory perspective, what dependencies are there. So I would like to talk about the problems faced in the data center today. Especially we look into first I'll start with that, we look into the role AI/ML infrastructure is playing into this and other services are playing as they are growing, and the technological challenges faced by memory specifically to enable these. And once I talk about problems, Chris will take us through the solutions and what we are exploring at Meta and the future direction in general. Finally, we would like to talk about the OCP project. I don't know how many of you listened today morning, but the work for composable memory system is now a formal sub-project under server track. So we'll talk about that and talk about the open community. So with that, let me dig in. Let me start talking about the role AI is playing in today's infrastructure. Now, we meet a new friend in cafe, friend of friend, and we remember them by how they look, how they speak. In general, essentially, we are putting together a canonical presentation of that person in our memory. And this is what training is all about, right? You're training that what we are like to build the identification model. And then after a few months later, or maybe a year, or maybe 2 years this time, we meet at OCP and we say, we remember, oh, I know this face. It's a friend of friend that I've met. You are searching your memory, and voila, you remember the name of that person. And this is what the inference is all about. Right? You're searching the instance and that model against what has been stored in your memory. AI goes beyond that. You build that, trained all those models, but then it can create new models by itself that don't exist. So this is the creation of new ideas. This is what we talk about synthesis. So all these trainings, search, and synthesis, these are the AI/ML use cases that are actually driving, big drivers of data center as we see into the future and what is exactly those requirements are being driven. So the major AI data center, let's talk about classification for these AI services that we run in our data centers. They come into 3 broad categories: ranking and recommendations, computer vision, and language. So recommendation system, this is where lot of significant infrastructure depends for us. This is the underpinning the product capabilities for search and ranking results and making video suggestions. Whereas vision, computer vision, which actually is built on CNNs, they are used for image classification, object detection, and additional video understanding, etc. And then finally, the language systems where you are doing the translation, whether it is a text or a speech, and then content understanding if you want to do subtitling, etc. So we categorize them then in this way because there are fundamental differences. There are a unique set of characteristics this requires in our infrastructure. And so if you want to build hardware which is optimized for these use cases, you really need to understand what the requirements are and then design the hardware so that we can define it for the kind of scale that we want to do. Now, the models that are most business critical for Meta are our deep learning recommendation systems, what we call as a DLRM. They are truly massive, on the orders of tens of trillions of parameters, just kind of a model that we are talking about, the features that you're training these models on. Training these models requires zettaflops of compute. So it is a huge expectation from infrastructure. Now, while Meta has some of the most sophisticated models in the world, we are not alone. Of course, the whole infrastructure is growing. There are a lot of demand being driven from that. This rapid scaling requires holistic cluster definition because there is a demand on the performance. Of course, it's not going to come free. It is going to have demand on infrastructure from cost perspective, but also from power perspective. And to make sure that we have most optimal solution, we need to start from data centers right up to the software that runs on the top and all the hardware layers in between. What we'll do today, though, we are going to make sure that we focus on the memory aspect of it, but each of the layer is a very important aspect of the overall design. So as you will see that the key difference in the shaping this definition of our future platforms and infrastructure is this whole optimization for this AI/ML infrastructure. Now let's zoom out a little bit and again come back to saying that what's our infrastructure, right? We talk about at a high level data center clusters are composed of storage and compute and memory, and they are connected over the network. Now these systems are optimized for meta use case. You want to maintain a small number of SKUs, so you want to make sure that you have optimal amount of compute or storage and then utilizing the network so that you have the right expected TCO optimization for the SKU. This requires optimal definition for handful of hardware SKUs that allow the economies of scale as we talk about hyperscale implementation. Over many years, the storage has been already largely disaggregated, and Meta has published its papers about how our storage disaggregation works, which allows scaling of compute and storage independently as the storage capacity is delivered over the network. Network has been designed to make sure it has the performance and capacity to make sure that it's not a bottleneck as we access the storage. However, one of the challenges that we have that remains so far is the strong tethering of compute and memory. They are always part of the same system due to the direct interconnect between CPU and memory. We talk about DDR, various generations. Now, this does lead into certain design constraints. So let's just double click on that and look at what various memory options we have, because these memory options decide what we are able to do from optimization perspective, from TCO as well as for the deployment. So this is this traditional memory pyramid, if you will, which allows us to do the capacity performance trade-offs. You go on the top, of course, you're going to have small capacity, but you'll have high performance, and then so forth, so on and so forth. On the right-hand side, what you'll see are the applications that they are more important for. Applications that need highest performance are going to optimize for processor cache, the best, most expensive memory that you can have on that there. Then you have GPUs kind of solutions which will require high bandwidth memory, which also need to have that much of memory at higher performance to perform at the expected level. DRAM is actually the primary layer for memory for today's compute platform, and they are designed as a key SKU definition parameter. If the applications need higher bandwidth or they need higher capacity, primarily you add more DRAM. Now, of course, there are some granularity of choice based on the DIMM capacity, number of DIMMs, or the channels that it supports, or the frequency of there are something, but eventually it's limited by those choices. You have limitations saying that on that DDR you're going to put this much of memory. So whether if you need bandwidth or capacity, you're going to continue to scale amount of memory on that application. The applications that need high amount of data per system, they want to achieve higher TCO. Sometimes these applications make service software changes that allow them to even spill over the data from memory to NAND. That's a choice they can make, but there are performance trade-offs that we are doing at that point. So NAND also becomes part of the overall memory pyramid today. Taking into a little bit detail about, we talked about those applications. Let's take only examples of two of them. One, of course, we talked about recommendation models, DLRMs. And we are going to dig more into as Chris talks through them. The performance needs of these training models as well as the size of training models. Both of them are actually expressed in terms of number of parameters you have for that training, as well as the kind of processing, the petaflops or the higher number that you're achieving on GPU. Both of them together decide how much memory you need per platform. So we are stretched to the limit of a practical amount of memory that we can put on such systems, 1P or 2P. As we continue to scale the accelerator performance as well as the number of parameters on the system, we are essentially stretched thin, and then we need good solutions. Caching and database systems, this is the second part of the application. These are slightly different. Caching requires you to have enough amount of retention time so that you can get a hit. That means you need higher memory per platform to make sure that you can achieve the expected goal for the QPS at a given retention time. Database systems, on the other hand, actually scale when you provide a lot of storage. But to make sure that that storage is effectively used, you need to achieve the certain queries per second. That depends on how much memory I'm providing. So to make sure that those platforms are most optimally designed from TCO perspective, you want to make sure that you have the right amount of memory, and all of them are driven. The TCO is significantly dependent on the options you have for putting the memory on those systems. Let me go back a little bit and talk about the AI/ML models and then two aspects of the challenges here. We talked about size of the model and then the performance requirements of the model. On the left-hand side, we are talking about how it is growing from the parameters perspective and how the memory is how much memory per accelerator is growing. As you can see, basically, that the memory per accelerator is actually growing much, much slowly than the need, in the sense number of parameters that are growing. On the right-hand side, we are talking about as the training cluster goes, how much is the performance expectation. So the clearly memory bandwidth, although the chart talks about memory and interconnect, I'm focusing only on the memory bandwidth here. Memory bandwidth, of course, is falling behind the performance needs of the platforms. So this does get reflected in our inference models as we'll talk a little more about DLRM as Chris talks to them for the deep learning recommendation models. There is another aspect which is very important for the scale, which is how is memory becoming part of our overall TCO math and SKU design math. So having looked at the fact that we have a need for large amount of memory capacity and bandwidth, sometimes together, sometimes independently, let's see how this trends weigh heavily on the TCO impact. So as we look over last 2 decades, while memory is cyclical in cost, as is most of the other technologies, the reduction for DRAM is more or less now flattening, as we can see on the right-hand side. So this, when added with the increased demand on the memory capacity and bandwidth, memory is now even more significant part of the data center cost. So as we build the next generation data centers, increasing core counts, new workloads that continue to drive higher memory capacity and bandwidth demands, leads us to talk more about important topic, data center memory systems. So we are going to look at it, how to solve it in innovative ways. So let me summarize the problem statement that where we are now, right? Data center memory surely faces following challenges. It has a need for scaling capacity, more than what's possible on today's compute tethered systems. Second is performance scaling, beyond what our current platforms allow. And innovative system designs optionality that helps drive the TCO efficiency across data centers. So the key phrase here is going to be the optionality. What choices do I have so that I can provide more memory capacity as well as bandwidth? So these are the problems that we are looking at and very looking to whole industry to join that. Let me give it to Chris, who's going to now talk through the Meta's approach as well as what OCP is doing in this area. Chris?
Thank you, Manoj. So now that we've talked a little bit about some of the challenges, let's see if we can do something about them. So unless you've been hiding somewhere, you've probably heard about Compute Express Link at this point. But just in case, I'll talk about it just briefly. CXL is an open industry standard that defines a set of protocols and interfaces that provide both high bandwidth, low latency, and coherency between devices. It's built on top of the PCI Express physical layer, which allows CXL to scale both in terms of link speeds and link widths, just as PCIe scales today. As we can now untether CPUs and memory controllers using CXL, we now have the ability to maximize system TCO by using a variety of potential media options and organizing them into different tiers. We can also do this in a standardized and media agnostic way, which lets us leverage the system integration aspects. We can apply CXL well beyond directly attached configurations as well. CXL gives us the capabilities to ultimately rethink system architectures and explore much more advanced memory systems. We can build pooled memory systems where multiple hosts can access memory regions on common memory devices. We can then extend this further by creating some of these regions as shared memory regions that multiple hosts can get access to. This allows those hosts to share common data or even results. Finally, with the emergence of CXL memory fabrics, we can build large-scale systems with shared memory and ultimately enable composability as well. Now that we've talked a little bit about memory tiers, how do we actually go about using them? Let's start by taking a look at the chart in the top left here. Across many applications, for example, caching, as Manoj was alluding to, or other applications such as data warehouse, we often observe that less than 40% of the memory in the system is utilized very frequently. This memory is referred to as hot pages. That leaves greater than 60% of memory as cold pages. This is actually a tremendous opportunity for us. It enables us to actually separate out those memory pages into hot and cold memory tiers. Hot pages are kept in native memory, and cold pages could be kept in CXL memory. However, There is a latency difference in these tiers, and that is something that we ultimately need to address. We believe that this should be done transparently so that application changes are ultimately not required to take advantage of this capability. One method to do this is at the kernel level, using a technique that we refer to as transparent page placement, or TPP. TPP will automatically promote or demote memory pages as needed so that the latency differences are hidden from the application. You can learn a lot more detail about this approach in our talk in the CXL forum on Thursday at 10:45. The other use case Manoj was talking about was for AI, so we can also look at doing memory tiers here. Specifically, let's have a look again at the recommendation models, and specifically the DLRM model that Manoj was alluding to. While these models have a lot of layers that require a significant amount of compute, and there's also a lot of interaction between different elements and between the different layers, these models are the ones that are often pushing the limits of both memory capacity and memory bandwidth. The two charts here show the bandwidth and latency requirements. The x-axis is the memory capacity, and the y-axis is the bandwidth in the top chart, and the latency in the bottom chart. On the top chart, the point highlighted by the purple number 1, for this point, we note that there's a considerable portion of the model that requires a large amount of memory bandwidth. And this generally resides in accelerator memory, most commonly HBM. But as we move farther down toward point number 3 here, we see that there's also a very large chunk of capacity that does not necessarily require that much memory bandwidth. It's equal to or less than main memory bandwidth, for example, from DDR5 DIMMs, and gets us close to what storage devices are capable of. This is also a good sign, as this is a characteristic that we can take advantage of. But it's not just about bandwidth again. Latency also matters. The main takeaway from the latency chart here is that the latency band is actually fairly small, which means that most of the accesses require a reasonably low latency. The application is tolerant of slightly higher latency than main memory, but it's definitely lower than what normal storage class devices could provide. So what are the key takeaways here? Given the fact that there's a fairly large portion of the model that requires fairly low bandwidth, a tier of memory beyond HBM and DDR5 could be implemented. So now let's take a look at what a potential system design might look like in this context. We can take a typical example dual socket AI system and add a third memory tier to it. So we have the accelerator memory, which is the HBM that's local typically on the accelerators themselves. Then we have the DDR5 main memory, and then we can add another tier here of CXL memory. Ultimately, with this CXL memory, we now have a way to continue to scale both memory capacity and bandwidth as those AI models continue to grow rapidly in scale, as Manoj was pointing to earlier. Okay, so let's circle back to this memory pyramid that Manoj was talking about. So we need to be able to address the scaling of both AI workloads, and we need to provide our broader set of applications with TCO-efficient memory on top of that. So by taking advantage of the model characteristics, we can apply a memory tiering approach. So if we take this typical storage pyramid, we can now start to see where things fit in, and as we start adding layers to what is normally a gap between DRAM and NAND SSDs. We believe that these new layers are best served with CXL attached devices, and in this context, we're referring to them as bandwidth memory and capacity memory. So now that we have a way to attach heterogeneous memory to a system to provide these memory tiers, we can take advantage of both the capacity and the performance trade-offs that we can make. In the AI use case that we've talked about today, it really falls into this capacity memory tier bucket. While ultimately the transparent tiering case that I was talking about falls more into the memory bandwidth tier case. So let's revisit the memory challenges that Manoj talked about. We can address the capacity and performance scaling through CXL memory expansion. And ultimately, we can scale even further as we use CXL for multi-host connectivity as well. Finally, we can continue to drive TCO efficiency by attaching heterogeneous memory as memory tiers. Of course, as we're working through all of this, it's important that we do so together as a broader industry because there's a lot of extra work in terms of both hardware and software development that needs to happen here. Thankfully, OCP provides us with an avenue to do just that. So today we're excited to share that the software-defined memory workstream is now graduating into a project under the OCP server track and will be renamed to the Composable Memory Systems Project. This gives us a place to explore a variety of these use cases and hopefully a lot more, and potential memory solutions and systems that we can apply to help address those use cases. A couple of the initial examples of memory solutions, and hopefully there will be a lot more on this slide in a couple of years, include memory expansion boards and memory modules. So when we talk about memory expansion boards, what we're talking about here, these are solutions composed of a board populated with a CXL ASIC, and they have some form of memory media slot on them. For example, one that would use DIMMs. Memory modules are much more self-contained solutions. So you can think of these as similar to the way an SSD is built and assembled and provided today. I'll leave you today with a few calls to action. First, help us tackle these memory challenges that we discussed today with both innovative hardware and software co-designed solutions. We've heard a lot about that this morning, and we do believe that's absolutely fundamental to helping us solve these challenges. Second, we really need to see more development around TCO-optimized memory. There's just not enough innovation in this space, and we'd really like to see a lot more of that happen. Finally, please join the new Composable Memory Systems Server subproject. Tomorrow, actually, we'll have a meeting here at the OCP Summit at 2:30, so please join us for that in the afternoon. And then also, if you're not tired about talking about CXL just yet, we have an entire forum on Thursday, so please join us on Thursday to continue the discussion there and hear a lot of additional perspectives. Thank you very much for joining us today, and we'll leave it at that. Thank you.
I think we may have a couple of minutes if there are questions.
If you could come up to the mic, though.
Just a quick follow-up. Can you just elaborate on what you mean by TCO optimized memory? Are you referring just lower cost memory, or is it something else you can elaborate on?
Well, I think cost is always an aspect, but it can't be the only one, right? So TCO typically factors in power consumption and usually is a ratio of performance to some other factor like power or cost. So it's really that aggregate packaging that provides you the TCO optimized portion.
All right. Thank you very much. Oh,
Yep.
There's one more question.
Come on up.
All right.
So whenever you were talking about the TCO memory, but then at the same time earlier,
Oh, okay. Yeah.
is that better?
A little bit. I don't think the
It's turned on maybe.
mic's not on.
Okay, maybe try again.
All right, go ahead. We're going to run out of time.
Okay, well, anyway, whenever you're talking about direct memory or pooled memory or shared memory, do you see the TCO memory applying to all three use cases?
Yeah, it absolutely can. I think you can apply some of the tiering concepts across any of those solutions, right? So you can decide how you want to combine them. I wouldn't view them as mutually exclusive, in other words.
Maybe just to tag on a little bit also to, as we talked about, Chris talked about the trade-off that we are ready to with capacity and performance, and I think that hopefully that's what can help us drive the TCO because we can get the newer heterogeneous solutions and other solutions that allow it cluster level optimization.
Okay, thank you.
Thank you, everybody.